Okay, this is going to be chapter 2 of the physics and technology of radiation therapy. Essentially, what we're going to be doing in this particular chapter is going over the physics concepts that you're going to need eventually in one form or another as we go through to learn how specifically radiation therapy can be used. So there are some simple concepts here that we need to go through in order to be able to get to the point where we can look at radiation and have a general idea as to how we can describe it using the concepts of physics. So here in the first section, you're going to be looking at units for certain physical quantities. So you've got SI units, a standard system that makes it a lot easier to be able to compute certain quantities. Any true SI unit is a combination of fundamental units listed in table 2.1. So these are going to be your fundamental units. Length is going to be the meter, mass is going to be kilogram, time is going to be seconds. Electric current is going to be the ampere. Temperature is going to be measured in Kelvin. Moles of is going to be the amount of substance, and luminous intensity is the candela. So these are going to be your fundamental units. Any other unit that we end up deriving from that is going to be something that you don't see in the list, but is something that you may or may not be familiar with. Newton, for example. Newton is going to be a combination of kilogram meters and seconds. As you can see there, it's kilogram meters per second squared, usually abbreviated with the capital N, which is, of course, going to be what we use for force. Examples of non-SI units are going to be electron volts, which you will see, ergs, rads, Rankins, those kinds of things. Even though the EV is not considered to be an SI unit, its use with the SI is going to be considered acceptable. One thing you will have to watch is whether or not you are doing correct dimensional analysis as you go through and try to compute several different units, because if you start mixing and matching and you're not careful, you'll end up with something that doesn't make any sense. So you'll also have units of quantity, which are going to be represented in a square bracket notation. So let's take force, for example. If you put it here in the square brackets, the unit for that is going to be newtons. Some standard prefix multipliers are going to be listed in the next table, and you can see here that when it comes to the prefix kilo, you can see what the symbol is going to be. So 1 kilometer is going to be 10 to the third times the fundamental unit there, which is meters. Mega, 10 to the sixth. Megahertz, is 10 to the sixth hertz. Giga, tera. You can see here centi, which is going to be used quite a bit. 1 centigrade is 10 to the minus 2 times gray. Milli, micro, nano, pico, that kind of thing. These are going to be the units that, or the prefixes slapped on different units in order to get the scale that we need. Mechanics is going to be the subject of the second section. Mechanics describes how material objects move. They're governed by certain laws, and those laws help describe motions of electrons in a waveguide of a Linac. And so that's how you can see this particular tie-in. There are certain types of quantities that we have in physics. One's going to be called a vector, and the other is going to be called a scalar. A scalar is a physical quantity that has no direction associated with it. So let's say something has 10 joules of energy. 10 joules of energy is a concept in which trying to introduce a direction makes no sense. So we don't do it. A vector, on the other hand, is going to be a physical quantity that does have a direction to it. So velocity, acceleration, force, those are all quantities that are going to have not only a magnitude, but also a direction. Since acceleration is going to be the change in velocity with a change in time, and velocity is a vector quantity, acceleration is also going to be a vector quantity. What you will also see with acceleration, if you're looking for just the units, again, that's the square brackets there around it. That's the same as the velocity divided by the time, and the units are going to be meters per second squared. When it comes to acceleration, if the body is moving in uniform circular motion, that object moves in a circular path with a constant speed. Even though the speed is constant, the object is accelerating because the velocity is changing. In other words, the velocity of something that is moving in a circle, while the quantity of the velocity may be the same, but the direction keeps changing. And this means that the acceleration is being pointed in towards the circle. So while the speed may very well be the same as it rotates around the circle, the velocity is going to change because of changing direction. The acceleration, tangential to the velocity, is going to be pointed inwards. This is called centripetal or center-seeking acceleration, and we'll go into that a little bit later on when it comes to particle accelerators. We move on from velocity and acceleration, and since we now know what acceleration is, we're going to use that definition, and we're going to use it to tell us what force is. So force is, this is according to Newton's second law, force is equal to mass times acceleration. If there is a net force on an object, in other words, if we look at all the forces acting on an object, and all of those forces end up with a certain amount of net force, in other words, you subtract out the stuff that's pushing against each other, and you find out what's left over. Whatever is left over is going to be considered the net force, and that is going to accelerate an object in a particular direction. The units of force is going to be the Newton. 1 Newton is going to be equal to 1 kilogram times meters per second squared. Now, force can have several different, can describe several different things that are acting on an object. One of those forces can be gravity. So the gravitational force exerted by the Earth on an object is called the weight. Now remember that the weight is going to be different from the mass. If you were to take an object on the Earth, it may weigh 10 pounds, but if you take it and you move it out into space, it may weigh nothing or close to nothing, but it will still contain whatever that equivalent amount of mass happens to be. So weight and mass are going to be two different things. And again, the SI units of weight is basically saying, what are the SI units of force? And again, those are going to be newtons. The older English units of weights are pounds, and that's what we normally encounter. It is technically incorrect to refer to the weight of an object in kilograms, as that is referring to mass. Okay, now that we know what force is, if we take an object and we apply a certain net force to it, and that net force goes over a certain distance, if we take the force, multiply by the distance, assuming they're headed in the same direction, it gets a little more complicated when they're not. When we multiply those two together, we get the amount of work being done on an object. That amount of work is going to have units of a Newton meter. A Newton meter is also referred to as a joule after a particular physicist, James Joule. This is referring to energy. In order to do work, you have to expend energy, and that's why this concept of work is necessary. Because we're going to take the joule, and we're going to discuss something called absorbed dose. How much energy is absorbed in a certain amount of mass, and that is going to be referred to as a gray. We'll get to that later, but this is where it's coming from. We're taking a certain amount of energy. Energy is necessary to do work, and that work or that energy can be categorized eventually and looked at if we divide it by certain things and whatnot, will eventually get us to the concept of absorbed dose. So that's how these concepts are starting to tie together. Work is one of those quantities that has a technical meaning that is different from the common meaning. In other words, if you were working very hard today, it's not quite meaning the same thing as the amount of work that has to be done in order to move a particular object. So say you've got if you were might be working very hard if you were standing stationary holding 100-pound weight motionless. According to the technical definition of the word work, the work done by you on this would be 0 because you haven't moved it through a distance. However, don't tell me you won't start getting some muscles there if you start holding 100-pound weight still and trying not to drop it over a certain period of time. Yeah. Okay, so we've gone from velocity to acceleration to force, and then from force to work, and then with work, we're also talking about energy. So now that we're building on those concepts as we go along, when work is done on an object, its energy is going to change. The energy is found in various forms. Kinetic energy is associated with motion. We describe kinetic energy using, and here it's described using the capital letter T, as 1/2 times the mass times the velocity squared. So this is going to be kinetic energy, energy of motion. And this illustration of work done on an object traveling in a straight line acted on by a constant force. You got a force here, it goes over a certain distance, we can calculate the work. The connection between work and energy is provided by the work-energy theorem, which states that the work done on an object is going from an initial state to a final state, and that's equal to the change of the kinetic energy. See, the amount of work that's done on a system, we take the total kinetic energy we have here minus the total kinetic energy that we had before, and that's going to end up being the difference. So now that we know what that difference in kinetic energy is, we can figure out what the work was done on an object. Was the work done on the object, did it add energy to it? Did it take away energy from it? That kind of thing. So if it starts from rest, in other words, the object isn't moving, this value might be 0, and therefore the amount of work that's done on it would be 1/2 times mass times the velocity squared. Units of energy are the same as those of work. Again, work and kinetic energy, we're going to measure that with the same type of unit. So the total energy of an isolated system has to be the same before and after an event. Energy can be transformed from one to the other, but the total amount must be the same before and after, and that's referred to as the conservation of energy. If it's isolated, the energy is going to be the same. It may change forms, but it's going to be the same. So now we've discussed work and energy. Now we talk about power. Power is going to be the rate at which work is done. How quickly are you able to apply it? The more quickly you can apply a certain amount of energy, the more powerful the system is said to be. So if work is represented with W, T is represented with time, then you take this divided by this, and it gives you the power of the system. And that's going to be joules per second, or the watt. So when you pay your power bill, what you're really paying for is the energy or work, but not the power itself. Power company expresses your usage in kilowatt hours, And it's a non-standard quantity that has the units of work because it's power multiplied by time. So if you take power multiplied by time, then you're getting the amount of energy. So electricity and magnetism. We've discussed force up to this point, but we've done it in a mechanical sense. We haven't really gone through and tried to apply it to electricity and magnetism, and we're going to need to in order to be able to get to the kinds of things that go on in a linear accelerator. So, how do we start representing these concepts in the realm of electricity and magnetism as opposed to mechanics? Well, we're going to start here with charge, static charge in this case. So the standard SI unit of electrical charge is going to be the coulomb. And the coulomb is, or the electrical force between charged objects, is going to be referred to as electrostatic or Coulomb interaction. So the force between two charged particles separated by a certain distance is given by Coulomb's law. So you got a certain amount of charge here, Q1, a certain amount of charge here, Q2, and the K is going to be a fundamental constant, which is, what we've discovered as characteristic of our universe. And so the force is sometimes called the Coulomb force or the Coulomb interaction. So if the charge on both particles has the same algebraic sign, in other words, if you have two positive or two negative charges, these are going to repel each other. If, however, they have opposite signs, then the particles are going to attract each other. So the Coulomb force holds electrons in the atoms. The electrical charge is said to be conserved. So total net electrical charge can neither be created nor destroyed, somewhat like the conservation of energy. An equivalent amount of positive and negative charge can be combined to give zero net charge. The total algebraic sum of the charge must be the same before and after the process. In other words, how much charge you had before is going to be the same as what you ended up after. That's total net. The first equation here only applies to point-like particles. In other words, both charges objects must be small in size compared to the distance r between them. So let's say someone rubs a balloon against your sweater on a dry winter day. If conditions are right, the balloon may stick to the sweater. The reason, of course, is that some of the electrical charge has been transferred between the balloon and your sweater. Both the sweater and the balloon started out uncharged, but the charge on the sweater and the charge on the balloon are equal and opposite, and therefore that causes the attraction between them. It cannot be directly calculated from the equation, but neither the balloon nor your sweater is small compared to the distance between them. The smallest amount of electrical charge is so-called the elementary charge. This is the amount of charge caused by a single electron or proton, and as you can see, it's pretty small. This number is going to be important to us as we study radiation physics. It's the smallest amount of free charge that's ever been detected. All measurable charges come in integral multiples of that fundamental quantity. Particles called quarks may have charges of maybe a third or two-thirds, depending on the quark. Single quarks have never been observed in isolation. They're always found in bound aggregates in which the total charge is plus or minus E. In fact, the standard model of elementary particle physics forbids the existence of isolated quarks. So an electrometer is frequently used in radiation therapy. You may have seen this being used in certain clinics where you've observed. And it measures small charges. So in a typical electrometer used in the clinic can measure charges as small as 1 picocoulomb. So now we've talked about force between electric charges. We're going to expand this concept a little bit and going into electric fields. We know charges exert forces on one another. We've just seen that. So the modern conception of that mechanism is that the charge is that charges establish electric fields in space, and that these electric fields exert forces on other charges. The force is mediated by the electric fields. So the electric field configurations are represented on paper, kind of like this. You've got a positive charge, and the field lines are always going to go from a positive charge out to a negative one. So you can see here you got a positive charge and you got the field lines all pointing out here. They are going to be headed towards a negative charge. So now we've talked a little bit about field lines and electric fields. What happens when the charges start moving? That's going to get us into the concept here of current. Electrical current is going to be the amount of charge that flows through some spot in an electrical device over a certain amount of time. It's going to be represented with I. I is going to be equal to Q over T, and the unit here is going to be coulombs per second, which is the same as an ampere. Here you can see the electrical field lines between two charged parallel plates. And a parallel plate is something that you're going to hear used in the clinic in order to measure certain things. So the plate on the left here, of course, is positive. Plate over here on the right is negative. The field lines go from positive to the negative. And you can see here that it's rather uniform going through. You got about the same amount, equal and opposite charges over here in that distribution. And so you can see as they go through, at every location between the plates, the electric field points in the same direction and the distance between the lines is constant. If they were starting to be clustered, then you would start to see that the lines might become stronger in certain spots and weaker in others. Now, back to current. There are two possible directions of current flow in a wire. There is a convention established before we discovered what an electron was. The current flows in the direction which is positive, in which a positive charge would move. We know that the electrons are the ones that really carry the charge in the current, so that we still stuck with that particular convention. So the current is always drawn in the direction opposite of the motion of the electrons, just to make things confusing. So figure 2.6 right here. You've got a very simple electrical circuit in which current flows from the positive terminal around to the negative, and it goes through the light bulb there as it makes its journey. The schematic is shown here. In other words, if we don't want colorful pictures or whatnot, we just want the basics of, hey, what's going on? We've got some sort of resistance here. We've got the current that's flowing from positive to negative, makes its way around. The resistance is inversely proportional to the amount of current that flows through the resistor, which is connected to the battery. The larger the value of the resistance, the smaller the current that will flow through the resistor when connected to the same battery. This is a symbol for an ammeter, and it's a device that measures the amount of current that goes through. And you can, again, you see the symbol there. It must be placed in series in the portion of the circuit in which current can be measured. An ammeter should have a low resistance so that it doesn't affect the current that you're trying to measure. An important parameter that must be set on an X-ray machine prior to exposure is the current through the X-ray tube, and that is represented in milliamps. Okay, so we've talked about charge, we've talked about current, and we've talked a little bit about energy. So can we loop some of those concepts together? Of course we can. We come up with a concept here called potential difference. If you've ever heard the term volts, this is where it comes into play. So you've got a potential difference between point A and point B. Then the potential difference between those 2 points in an electric circuit is the work per unit charge necessary to move a charge from A to B. That formula is given by this. The voltage is equal to the work divided by the amount of charge. So the work is going to be the work necessary to move the charge from A to B. The SI unit is going to be the volt or a joule per coulomb. This combination of units has a very special name. It's called the volt. And don't confuse volts with amps. Volt is a measure of potential difference. Amp is a measure of current. And you can see the voltmeter here. You've got A and B. You've got a current going through. So the current is flowing through this portion of the circuit. And notice that the voltmeter is connected in parallel with the circuit element for which the voltage is to be measured. The voltmeter should have a high internal resistance so that it's very little current is drained off of it. In other words, we don't want to alter what we're actually measuring. So there's a good analogy between charge flow in a wire and the flow of water in a pipe. Current is somewhat like water in that sense, or whatever the water flow rate happens to be, liters per minute. And the voltage difference is analogous to the pressure between the ends of the pipe. If the difference in pressure between one end of the pipe and the other is low, then the rate of flow of water is going to be low. In other words, if you don't have much coming out of the spigot from the house, you're not going to have much flowing through. But if you turn that up real high, then the rate of flow is going to be high. And so you can see the analogy there. So current will flow through an electrical conductor when a potential difference is applied across the material. Potential difference may be supplied by a battery or by the electrical power company. In normal material, the current drops rapidly to zero when the potential difference is removed. And this is because of electrical resistance to charge flow. So in 1911, the Dutch physicist Kamerlingh Onay, I guess is how you say it, made the stunning discovery: some materials lose all electrical resistance when cooled to very low temperatures, and that is referred to as a superconductor. The current established in a ring of superconducting material can persist for years with no measurable reduction. In other words, if you don't have any resistance pulling those electrons out, you can continue on. And that current is not ever being diminished, and that's what's going on here. So the temperature below which a material becomes a superconductor is called the critical temperature. Solid mercury becomes a superconductor at 4.2 Kelvin, which is extremely cold. So the need for very low temperatures makes superconductivity difficult and expensive to achieve. So a common method for attaining the necessary low temperatures is to use liquid helium. The boiling temperature of liquid helium and atmospheric pressure is 4.2 Kelvin. And up to 1985, the highest known critical temperature was 23 Kelvin for rubidium and germanium. I forget exactly what that compound is. In 1987, a new class of superconductors was discovered having a critical temperature of about 90. Such temperatures can be reached by using liquid nitrogen rather than liquid helium. Liquid nitrogen, being much cheaper and easier to work with, is what's helping. As of this writing, liquid helium costs about $5 a liter, whereas liquid nitrogen costs less than 1/10 of that. Unfortunately, the new high critical temperature superconductors are ceramics and as such are not easily fashioned into wires. Maybe we'll make some more improvements on that as time goes on. High voltages are generally, but not always, dangerous. The amount of danger presented to a human being is related to the amount of work that the electricity can do. So if we look at equation 2.14, we can see that this depends on the amount of charge that moves through the potential difference. Static electricity is associated with high voltages, but very low currents. If the current is low, then very little charge moves across the potential difference. When you receive a shock from a doorknob, there may be a readily visible spark. The voltage associated with such static charges are quite large, perhaps several thousand volts. Compare this to the volts supplied by a household battery, or the 110, 120 volts you get out of the electric outlet. Very little charge is transferred between your hand and the doorknob when you receive a static electricity shock, and therefore little harm is done. The electrical outlet, on the other hand, the voltage is far lower, but you've got a lot more amps that can run through you. So it's not the voltage that can kill you, it's the amps. Linear accelerators are used in radiation therapy clinics, make use of high voltages that are extremely dangerous. In other words, don't go monkeying around in there if you don't have to. High currents can be delivered. That's why you get the other service personnel involved. That way you don't have to worry about it. So the electron volt is a unit of energy, not voltage. So the SI unit of energy is the joule, and it's very unwieldy for a discussion of atomic and nuclear physics. It's just too large. Therefore, we introduce a special unit that is natural for that state, and that is the EV, or the electron volt. So imagine two parallel charge plates, as in figure 2.9, one positive and one negative, kind of like what we've got going on here. Let us suppose that the potential difference is 1 volt. If an electron is placed at the surface of the negative plate, it will be accelerated towards the positive plate. Work will be done on the electron, and therefore its kinetic energy will change by an amount of this. So the change in kinetic energy is equal to the same as the work. And if you remember our definition of voltage, it was work divided by the charge. If we multiply both sides by the charge, then we find out that the work is equal to Q times V. We know what the elementary charge is of an electron. Multiply that by the voltage that's in between these two, which we were told was a volt. So we get 1.6 times 10 to the minus 19th Coulomb volts. We know that 1 volt is equal to 1 joule per Coulomb. So we know that the change in the kinetic energy is going to be 1.6 times 10 to the minus 19 joules, and this is how we define it. 1 EV is going to be equal to this. So an electron volt is the amount of energy gained by a particle with one elementary unit of charge, which is accelerated through a potential difference of 1 volt. The amount of kinetic energy acquired by a charged particle accelerated through a potential difference V is going to be this. So we have the amount of kinetic energy here in electron volts. We have charge divided by E multiplied by the number of volts. That gives us the kinetic energy. The mass of the particle does not affect the change in kinetic energy, only the charge. The mass does affect the final speed of the particle, and the more massive particle with the same kinetic energy will have a lower speed than a less massive particle. An electron volt is not the same as a volt. Volts are not energy. It is common to deal with particle energies of the order of thousands or millions of electron volts, and that's why we have the prefixes as we discussed before. Okay, so up to this point, we had talked a lot about electricity, but we mentioned electricity and magnetism earlier. So how does magnetism play into this? Well, a moving charge or current will produce a magnetic field. And there's a lot more information on that later on, but let's just settle for this right now. In magnets, such as those found holding papers or a refrigerator or a filing cabinet, the currents are microscopic in nature and involve the motion of electrons and atoms. They're permanent magnets that are made from materials that retain their magnetism more or less permanently. Permanent magnets generally contain ferromagnetic elements, iron, cobalt, and nickel. A current carrying wire can also produce a magnetic field, and that's the basis for the electromagnet. So the vector B describes the strength and direction of the magnetic field. So when you see B there with a little vector notation on it, that's going to be talking about a magnetic field. The strength is related to how hard the magnet pulls on things. And the direction can be determined by use of a compass needle or iron filings in order to take a look and see what the magnetic fields look like. The convention is that a magnetic field points away from the North Pole and points towards the South Pole. The SI unit of magnetic field strength is going to be the Tesla. Not the car, but the unit Tesla. The Earth's magnetic field strength is about 2.5 times 10 to the minus fifth Teslas. A very strong permanent magnet might have something as high as 0.5 Teslas. Permanent magnets are incapable of producing field strengths much larger than this. If you're going to produce higher field strengths, electromagnets are required. An electromagnet can be made by winding a coil of wire around a piece of iron. When a current passes through the wire, the magnetic field is generated. An electromagnet made with superconducting wire, such as what's used in an MRI, can produce field strengths of 4 Teslas. Draw that in comparison to what we were reading up here. This requires liquid helium to reach the critical temperature. A 4 Tesla magnet is very strong, strong enough to tear a wrench out of your hand at close range. Not to speak of erasing magnetic information on credit cards. So whenever entering an MRI room, be sure to divest yourself of all metallic objects and credit cards. Some of the pictures I've seen out there of gurneys and whatnot being drawn into an MRI are pretty impressive. So those are some pretty strong fields. So we've got an example here we're going to work through. So I've got a proton of a certain mass and a charge of plus E is accelerated from rest through a potential difference of 1,000 volts. So calculate the final kinetic energy and speed of that particular particle. All right, so we know how to find the kinetic energy. It's Q divided by E times the number of volts. We know that it's 1 proton, so it's 1E divided by E times 1,000, so that gives us 1,000 electron volts. So that's our kinetic energy. We also know that the kinetic energy can be described as saying 1/2 times m times v squared. When we solve for v, we come up with this equation. Velocity is equal to the square root of 2 times the energy, kinetic energy divided by the mass. Kinetic energy units must be converted to joules before substituting into this equation. If you don't do that, then you're going to end up with gobbledygook on the other end because the units won't work out. So therefore, the velocity is equal to 2 times this, which when we take 1,000 eV and we make the conversion here, we find out that's that number of joules divided by the mass, and it ends up being 4.4 times 10 to the 5th meters per second. That's moving at a pretty good clip. If we take all of this and we repeat it for an electron, running through the same thing here, we end up, of course, with 1,000 eV. Again, we were using 1,000 volts at the beginning. We take this energy, put it in here. We're dividing by a different mass, so we can see here that the velocity here is much faster, which is what the book was alluding to earlier. So if we have a carbon ion that's accelerated through a potential difference of 30 million volts, what's the final kinetic energy of that? The atomic mass number of carbon is 6, and therefore a fully carbonized ion has plus 6e. Because of that, we put in 6e here for the charge, divided by that, multiplied by this, and we come up with 180 MeV. That's a lot of energy. So, a charged particle at rest in a magnetic field experiences no force due to the magnetic field. If a particle starts to move, however, it will experience a force. And the notation in this book for magnetic fields perpendicular to the page is this for magnetic field pointing out, just like coming straight at your face. And this is a magnetic field pointing in to the page, in other words, going away from you. One way that's been commented before as to how to think about this. This represents an arrow that's coming at you. It's got the point that's coming at you. This is like an arrow that's going away, looking at the fins on the back of it. This figure is describing an electron which enters a magnetic field that's going into the page. The circular, you can see the circular symbols there. At the instant the electron is at the position shown, its velocity is towards the lower right. At that point, it experiences a force towards the lower left. In other words, it's got a velocity going through. There's a little bit more to this than just what meets the eye. It's a little bit more of a mathematical technique than what I want to go into. Just know that when this charge is moving through, if you work through the math, you find out that the force is pointing in this direction. Why is that important? Why should you care? Well, you've got an electron beam coming through the linac like this. It encounters a magnetic field, which is going into the page. That's going to experience a force pulling on it this way. So its trajectory is going to change and eventually point down towards the patient. This is the equation that dictates what the amount of force is going to be. Now, this assumes that a lot of these things are at right angles to each other. But this will give you the quantity of the amount of force that's being exerted. Again, the math there is a little bit more descriptive than what's being talked about there, but that's what's going on, and that's why it applies in this particular case. So, the electromagnetic spectrum. What does this have to do with us? So, it talks a little bit here about light and what a mystery it was. The speed of the transmission of light in a vacuum was also known in the mid-1800s. James Clerk Maxwell, really interesting character, developed a set of differential equations known as Maxwell's equations that summarize all of our basic knowledge of electricity and magnetism. He noticed that the equations have a solution that is wave-like. The waves are undulations of perpendicular electric and magnetic fields that propagate through space. Out of curiosity, Maxwell calculated the speed of these electromagnetic waves from basic constants of electricity and magnetism. He found that the speed of light was 3 times 10 to the 8th meters per second. This was unexpected and a dramatic demonstration that light is an electric and magnetic wave that travels through space at this speed. This marked a pretty big triumph. Nobody had ever previously suspected that light had anything whatsoever to do with electricity and magnetism. This ended up leading to the discovery of radio waves. Electromagnetic waves are generated by accelerated charges. You can see radio broadcast aerials or towers throughout the nation. These produce radio waves by driving oscillating currents up and down, and light is just one example of an electromagnetic wave. And it is only a small part of the whole spectrum of electromagnetic waves, which include radio, infrared, and ultraviolet and X-rays. All electromagnetic waves travel at the same speed in a vacuum. If they're not in a vacuum, it'll travel at a different speed. The type of electromagnetic wave, whether visible, radio, is determined by the wavelength. The wavelength is given by lambda, and it's the distance between crests or troughs. The wavelength of light will determine its color. Visible ranges in the wavelength from 400 up from red for violet up to, 400 for violet and up to 700 nanometers for red. Green's in the middle of about 500. Frequency is going to be the opposite in a sense. It's going to be how quickly do a certain number of troughs or crests go by an observer per period. How quickly does it move? The units there are going to be seconds raised to the -1 power. It's also going to be called hertz. For an example, if a wave has a frequency of 5 hertz, you can count 5 crests per second as it passes you. And that applies to all types of waves. The relationship between frequency and wavelength is this, and since we're dealing with electromagnetic wave, if you multiply the two together, you get the speed. So to get a better feel of the variety of electromagnetic waves, you can see the spectrum here. You've got radio waves here with the frequency here, or the wavelength, I think is what's being measured. Yeah, the wavelength here, that's what's being measured. the microwaves, infrared, you've got the visible spectrum, you've got ultraviolet, and you got gamma rays. So these are going to be the wavelengths of all of these. You can notice these are really long, these are really short. As the wavelength gets larger, the frequency here is going to get smaller, because if this is going to be the same and this value is going to be getting larger than this value, in order to make this equation still hold true, this has to get smaller. So that's what's going on here. Infrared radiation has wavelengths that are somewhat longer than visible light. Although you can't see infrared, you can feel it if it is strong enough. It's the infrared radiation component of sunlight that makes your skin feel warm. Ultraviolet radiation lies between 200 and 400 nanometers, just right above the visible spectrum. And you can see where UVA, UVB, and UVC all have their definitions. There's no real physical distinction between those other than slightly different wavelengths. But the differences lie in the biological effect. Human skin is relatively insensitive to UVA, but very sensitive to UVV and UVC. The atmosphere filters out all of the UVC. It is UVB that usually causes sunburns and promotes skin cancer. UVA is used to produce tanning in tanning salons. It is now believed that exposure to UVA is not as harmless as previously thought. UVA is deeply penetrating, and it penetrates the skin epidermis to reach the dermis. Excessive exposure to UVA is likely to produce premature sun-aged skin. X-rays have very short wavelengths, and it's used for medical diagnostic purposes and has a wavelength of roughly 0.1 nanometers, about the size of an atom. Its distinction between gamma rays is one of origin, not so much energy. Gamma rays, these electromagnetic waves, must originate in an atomic nucleus or from positron annihilation. There aren't really any gaps in the spectrum. It's continuous. The divisions between various types, such as radio waves and microwaves, are somewhat arbitrary because of the continuous nature of the spectrum. At the beginning of the section, we promised to give two answers. What is the physical nature of light? And the first answer is that light is an electromagnetic wave. Experiments conducted in the late 1800s and 1900s led Albert Einstein to speculate that light sometimes acts like a particle. In this light, as well as ultraviolet, X-rays consist of massless particles called photons. It took Einstein's bold genius to assert that an entity can act both like a particle and a wave. The photon is a neutral particle. The modern picture of light is that it's an entity that can sometimes act like a wave and sometimes act like a particle. In any given experiment, it acts as either a wave or a particle, but never both. The energy of a photon is proportional to the frequency, and that frequency is multiplied by Planck's constant. And you can also turn around and relate it to its wavelength as well. Okay, so you've gotten a brief view of a lot of physics that have led us up to this particular point. Now we're going to take a look at how the special theory of relativity plays into this. In 1905, Einstein published a paper that was entitled "On the Electrodynamics of Moving Bodies." In this paper, you had the special theory of relativity that was laid out. And the paper showed that the speeds comparable to the speed of light, or at speeds comparable to the speed of light, the laws of mechanics as established by Newton, and those that followed him don't work. Einstein developed a new theory called special relativity. Newton's laws emerge as a special limiting case where speeds are small compared to the speed of light. In other words, you're looking at something that is much, if the velocity divided by the speed of light is much less than 1, generally anything that is considered to be around a tenth of the speed of light or whatnot will still be approximated pretty well by Newtonian mechanics. You start getting above that, then Newtonian mechanics starts to break down. Theory could not possibly be correct otherwise. Newton's laws of mechanics have been tested at speeds that were small compared to the speed of light for about 200 years, and they kept working, so everybody just kind of kept going with them. The problem is you're testing at a particular point at which which you're able to apply this. You start increasing the speeds, things start changing. Examples of the highest speeds that we ordinarily encounter are a jet aircraft, about 600 miles an hour, which is about 270 meters per second, and the speed of the Earth in orbit around the Sun, which is considerably faster than the jet, about 3 times 10 to the 4th meters per second. They're both much, much smaller than the speed of light. So the special theory of relativity has some fascinating and bizarre effects like time dilation and the universal speed limit. The prediction of time dilation says that moving clocks run slow. So an example is going to be, say you've got a pair of twins, one of whom leaves Earth in a rocket ship at high speed, and the other returns many Earth years later, having aged only a few days. The twin that stayed behind is now an old man. This is not speculation. This has actually been measured. Experiments have been done in which 2 atomic clocks are synchronized. One of them is aboard a jet aircraft and flown around. When the 2 clocks are brought back together again, the one flown on the jet reads less elapsed time than the clock that stayed at home. The difference is small because the speed of the jet is small compared to the speed of light. The amount of the difference agrees very well with the predictions of the formula of special relativity. It's really some weird stuff, but that's how it works. So we're going to look at 5 key results here of this theory. Speed of light in a vacuum is constant. No material object can travel faster, or for that matter, even at the speed of light. But you can get close. Number 2, an object's mass increases with its speed. We don't notice this effect at everyday speeds because it's so small, but it provides an explanation of this. As an object's speed increases, its mass increases, and then it becomes more difficult to accelerate. As the object speeds approaches c, its mass increases without bound and becomes impossible to accelerate further. So the mass of an object at rest is called its rest mass. Mass can be converted into energy. This equation right here is about the most famous that you will ever see. E is going to be the amount of energy. M is going to be the amount of mass. So you can see here that with thermonuclear fission reactions, you convert this number of kilograms of the sun's mass into energy every second, and it provides the radiant energy that we see all around us. In nuclear reactors, nuclear fission slowly converts small amounts of the mass of uranium into energy. Nuclear weapons I don't even really want to talk about because it's pretty depressing. But what you are seeing here is that mass and energy are interchangeable. You just got to know how to make it work out. So the rest mass of a particle can be expressed in terms of energy since they're equivalent. If you have a rest mass of basically the mass of an electron, the energy is going to be equal to that multiplied by the speed of light squared, or that number of joules. If you put it in MeV, this is what it turns out to be, 0.511 MeV. Number 4, total energy of a particle is the sum of its rest mass and its kinetic energy. And note that this, number 5, is not equal to 1/2 mv squared unless v is much, much less than c, and this m sub 0 is the rest mass. We don't need to be concerned with the relativistic expression for t. If the kinetic energy of the particle is a significant fraction of the rest mass, or if it exceeds the rest mass energy, then the particle must be traveling close to the speed of light. So those are all of some basics there regarding the special theory of relativity. The basic takeaway that I want you to have is that it relates mass to energy. Next, we need to take a review of the atomic structure. So by 1900, we knew that electrons existed, and the existence of atoms had been fairly conclusively established. Prevailing model at the time was due to J.J. Thomson, which is the discoverer of the electron, and he thought it looked like plum pudding. And to give you an idea, this is the plum pudding model. You have basically your atom here, and you have a bunch of electrons just kind of scattered around in there like plums in plum pudding. That's how they thought it looked. A total positive charge and a total net charge of all the electrons balanced to leave it with a charge of 0. And that's the other thing I need to describe about that. The blue here is going to represent the electrons, and this red is going to represent the positive charge, which is they just thought was just kind of scattered around in there in some sort of cloud. So that was the model going up until about 1909, when Geiger and Marsden, working under Ernest Rutherford, started saying, okay, well, let's find an experiment and let's see if this is actually true. So they took thin foils of gold, and these thin foils had various substances with alpha particles. Most alpha particles passed through the foil and were deflected at small angles, kind of like what you see here. And it's consistent with an explanation based on the plum pudding model. If the positive charge is smoothly distributed throughout the atom and the electrons are very low in mass compared to the alpha particle, then you wouldn't expect large deflections in the trajectory. In other words, as you shoot this through, all you should see maybe are some of these small deflections. In the same way, one does not expect a running elephant to be deflected by a mosquito. It just doesn't happen that way. But every now and again, as they ran this experiment, very large deflections up to 180 degrees were observed. They didn't know exactly how to explain it. Quoting Rutherford, it was quite the most incredible event that's ever happened to him. It was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So, Rutherford developed a nuclear model of the atom in 1911 based on data collected from alpha scattering experiments. And in this model, all the positive charge and almost all the mass is concentrated in a single dense region called the nucleus. The electrons are of comparatively little mass and are distributed around in the nucleus. So with that framework, occasional large angle scattered of alpha particles occurs when a positively charged alpha particle passes too close to a small, relatively massive atomic nucleus. And since it's very small in comparison, this happens very infrequently. And now it's known that atoms typically have a size of 10 to the minus 10th meters, and that the nucleus is 10 to the minus 4th meters. And most of humanity is considered to be empty space. Nuclei are composed of protons and neutrons, which are collectively referenced as nucleons. And a proton has a single unit of positive elementary charge. The neutron is neutral, and the number of protons is called the atomic number, and represented by Z. Hydrogen has a Z is equal to 1, uranium is equal to Z is 92. Total number of nucleons is going to be called the mass number. In 1912, the Danish physicist Niels Bohr was a visitor in Rutherford's lab. He published a model of the hydrogen atom in 1913 based on his research in Manchester. And this model has since become known as the Bohr model. In the Bohr model, the electron orbits the atomic nucleus. The Coulomb attraction between the positively charged nucleus and the electron provides the force necessary to keep the electron in its orbit. It explained some features of the hydrogen atom, but it left many unexplained, and it couldn't explain the properties of multi-electron atoms. This got revised a little bit later with quantum mechanics, and the Newtonian mechanic is not valid in the microscopic world. In the larger macroscopic world that we inhabit, Newtonian mechanics emerges as a special limiting case of quantum mechanics. All of modern atomic, nuclear, and elementary particle physics is based on quantum mechanics. Quantum mechanics provides the framework for the very detailed analysis of atomic structure. Simplified picture describes electrons as orbiting the atomic nucleus. This depiction undoubtedly originates from the observed structure of our solar system, and you can't take that quite as rigidly as you might like. But electrons are said to occupy certain shells or orbits, and these are categorized by the quantum number n, which you see here, and begins with k. Why? I don't know. Each shell can only hold a certain number of electrons. Generally, the shells are filled in turn by electrons as we go through the periodic table. This K shell holds 2, the L shell can hold 8, M can hold 18, and it goes by 2 times n to the second electrons. So in other words, if for the M shell, it can hold 18 electrons if you put 3 in here for this. Electrons residing in an atom cannot have just any old value of energy. They're only specific discrete energies. Electrons in different shells have different energies that are unique to the element. The energies are represented by negative numbers to indicate that the electrons are bound to the atom. In other words, a positive amount of energy must be given to the atomic electron to free it from the atom. So electrons in tungsten have an energy of approximately minus 70 keV. To free the electron, you have to give it 70 eV. After the electron receives this amount of energy, it will have 0 kinetic energy. It will be free from the atom, but it's kind of stuck out there. If it were to receive 90, then it would be freed and would be left with kinetic energy of 20 eV. Electrons in inner shells are more tightly bound to the atom than electrons in outer shells. An atom can be thought of as a little like a water well. The electrons occupying inner shells are deep in the well and take more energy to remove. The higher the atomic number, the more tightly bound the electrons are. Binding energies are roughly proportional to Z squared. Physicists use energy level diagrams such as 2.17 to illustrate this. Ground state of an atom is the lowest possible energy configuration. All electrons are in the lowest state possible. An excited state occurs when one or more electrons occupy a higher energy state than if they were in a ground state. So you're kind of seeing here in this particular diagram an energy level from a tungsten atom, shows the energy of the shell. It requires 70 eV to remove a K shell electron from a tungsten atom. Only 11 here, only 2.5 here. And they can transition between shells. A transition from a lower to a higher energy state occurs if the atom absorbs an amount of energy equal to the difference between the shells. This could happen as a result of a collision between the atom and another particle, or by absorption of a photon with an energy equal to the difference between those two levels. So here's an example of an electron making a transition from a K to the L state. The atom is left with excess energy and is said to be in an excited state. An electron makes a transition from M down to the K. When the electron makes the downward transition, the photon is emitted with energy equal to the difference between those two. So, an electron makes a transition from the M shell of a tungsten atom to the vacancy in the K shell. What is the energy of the emitted photon? Well, if we go back through and we look at figure 2.17, energy of the K shell is minus 70, and the energy of the M shell is minus 2.5. If you take 70 minus 2.5, this is the energy of the emitted photon. What is the wavelength of this photon, and what portion of the electromagnetic spectrum does it reside? To find the energy, here we know what H is, and we can determine what the what the wavelength is. We know this, if we put it here, we know how many eV that is. Once we solve this particular formula for the wavelength, we put that information in. This is the wavelength. And so this is the X-ray part of the spectrum. So the number of electrons and their configuration determine the chemical properties of the element. Chemical reactions involve the sharing or exchange of outer electrons between the atoms. Energies associated with atomic processes, such as chemical reactions, are on the order of a few electron volts, whereas energies associated with nuclear processes are in millions of electron volts. Okay, so what is radiation? We've gone through a lot of physics here, but what is radiation? The term radiation is confusing. Physicists often refer to any type of radiant energy flow as radiation, so gravity waves, predicted by Einstein's general theory of relativity, are considered to be gravitational radiation, or you could be the 3-degree cosmic background radiation that is a remnant of the Big Bang. When used in a colloquial context, the term radiation generally means ionizing radiation, radiation that is energetic enough to cause ionization of matter. The cosmic background radiation above is not even close to energetic enough to cause ionizing radiation, or to cause ionization. Ionizing radiation can consist of energetic charged particles such as electrons, protons, alpha particles, or neutral particles such as photons and neutrons. In Chapter 6, we'll be describing how these particles cause ionization. Ionizing radiation can be very biologically damaging. The smallest atomic ionization energies are on the order of about 5 eV. So from the wavelength of 5 eV protons is 250 nanometers, which is in the UVC band. Radiation that is not energetic enough to cause ionization is referred to as non-ionizing. Non-ionizing radiation can also cause biological damage if the rate of energy is high enough, such as with infrared radiation. If the level of radiation is high enough, it can cause heat production sufficient to lead to burns. So here are some problems. At the end of the chapter, I will get these typed up in an electronic format so you can kind of go through and you can work on them on your own.